acceptance.
Okay, so welcome. We're a quite small crowd, which means the presentation gets a bit more personal, so I like that. First off, I would like to apologize. If you came here thinking you would watch the presentation Thawing Java on Amazon Lambda, reducing cold starts from 11 seconds to 1, I've had to change that due to recent events. So when I redid the benchmarks, it turns out this isn't accurate anymore. We're going to do the completely different presentation, Thawing Java on Amazon Lambda, reducing cold starts times from 6 seconds to 0.2, which is, yeah, even better. Like, relatively, I think, what's that, like that 3,000% or something faster, instead of like the measly 10 times faster. So this is the better talk, right? So my name is Ranis. I'm a coding architect at Factor 10. We're a small software consultancy in Sweden. We specialize in software, and we let our customers specialize in whatever they specialize in. So, quite general. I'm not on Twitter or anything. I am on Mastodon, because I'm a Twitter dropout. You can follow me there if you want to. I also have a blog where I write about stuff. So, something about me. I had trouble making an About Me slide, by the way, so I just stole these from our webpage. So I have a Master of Science degree from Lund University, Faculty of Engineering. I wrote my master thesis on performance and cost-efficient cloud architecture, and I wrote that in 2008, or I started in 2008. So I've been working with Amazon Web Services for 15 years, which is quite some time, I think. I'm an active triathlete, or at least I pretend I am. I still have the suit. I haven't done a triathlon in like 3 years before the pandemic. I still know how to swim, I still know how to ride a bike, and I don't know how to run, so maybe I can get away with it. I'm in the top 4% of Stack Overflow, which is basically just me saying I have more rep than you on Stack Overflow. And I work for Sony Mobile, and they sent me to Tokyo to teach my Japanese colleagues about cloud. And I also brew beer and bake sourdough bread. So if you want to know anything about beer, please come up and talk to me afterwards. I can mansplain everything about beer. Anyways, back to the presentation. So we're going to do a Lambda function, and we're going to take it on a journey. So our Lambda function is fairly simple. We have our client over here, which might be web application of some sort, browser calling into a web API. I'm going to just use the Lambda API to simulate the client. We have our Lambda function. And the client sends a user object. It's just a JSON object with a name. The Lambda function adds a unique ID, and it stores that in DynamoDB over here, among all the other uses that we're going to shove into our database. So when I write Java applications, I usually reach for my go-to framework, and that's Spring. I don't think I have to explain what Spring is. Spring is everything. There's a Spring module for basically anything you want to do. And of course, there is one for Lambda, and it's called Spring Cloud Function. So I implemented my Lambda function with Spring Cloud Function and the Amazon SDK for DynamoDB. And if we look at the call graph of that, it looks like this. So we have Lambda up here. This is the Lambda runtime. Somehow, it calls into the Spring Cloud function. We don't really care about how that works. That's just, we get a request and we handle it. Spring Cloud function, in turn, it sets up the Spring context, and it wants to get the handler from the Spring context, which is dependency injected. And we get our handler, and the Cloud function then calls the handle method on our handler, which then takes the user object we got, adds an unique identifier, stores it in the user repository, because we do follow domain-driven design, right? We have a repository. We don't talk directly to our databases from our business logic. And the user repository then, in turn, translate the save method into a put item call to DynamoDB. And then we return all the way back to the user, which gets the newly minted user object with a unique identifier. So let's benchmark this. And it looks good, right? All good down here in the 50 millisecond range. Apart from, yeah, this one. It kind of stands out, doesn't it? So this right here, that's the entire reason I'm here in front of you talking. This is a cold start. So a cold start means that there wasn't an instance running of your function. Amazon had to start a new JVM, load your application code, and then you could call your function. And these happen, like if you ask Amazon, they're not going to tell you when these happen, but because they shut down your function at their, like when they feel like it doesn't need it anymore. So when no one calls your function, it goes down to 0. There's no active instances of your application. But also, if you have a spike in traffic, they scale up, you get cold starts, and traffic slows down, they stop the instances they started, and when you get a new spike, you get new instances. So cold starts happen from time to time. And we're going to explore a bit when they might happen. So this is a architecture diagram that I stole from the Amazon documentation. It shows a single-page web application for some ticketing system, I guess. Maybe it's a local theater or a cinema or something. Let's say it's a theater. And we have Amazon API Gateway, which calls a bunch of Lambda functions, and we also have a Lambda authorizer. So these 4. So what happens when someone goes in and visits this page is they're going to hit all these 4 Lambdas, and then they get shown a page with theater shows, right? So imagine this is a local theater, not that much traffic. People generally visit your page in the afternoon. They get home from work. They want to go to theater on the Friday maybe, and they check out your tickets. And then they go to bed, and nothing really happens during the night. Maybe someone wakes up in the morning, have their morning coffee, see, is there any good shows on Friday? And during the night, since no one has called your API, all your Lambdas are scaled down to 0. There is no instances running at all. So what happens is this person sits down, they have their morning coffee, and they hit your web page, right? So the web page is going to call into the API. And the first thing that happens is we hit the Lambda authorizer. So this is the authorization function that checks that this user is actually logged in. It's allowed to call our API. And that's not running. So we get a cold start. So after 6 seconds, we know that the user may actually call the next Lambda function. So API Gateway goes ahead and it calls the shows Lambda, which returns all the shows from the database. Now, that's not running either. So that's another 6 seconds. So after 12 seconds, we have a list of shows. Okay, so the UI displays the list of shows. And then, of course, it needs to display some information about the shows as well. So it calls the API. We hit the Lambda authorizer. Now, this is running. So this takes 50 milliseconds. That's fine. We move on. We move on to the info Lambda. And yeah, that's not running. So we wait another 6 seconds. We get some information. And then the UI goes, and it wants to show tickets, right? So same thing happens again. We call the Lambda authorizer. That's warm, 50 milliseconds. We go to the tickets. Yeah, that's not running. That's another 6 seconds. So after 24 seconds, we have our web page. Now, by that time, whoever's drinking their morning coffee probably decided, yeah, I'd better off go to the cinema. So you lost that one. You lost them. Whoever comes around next, everything is warm and running, and they get their page quickly. But the poor person who had to wait for 24 seconds, we can't have that. So if we look at the call graph again, what's happening? Well, this is the warm case, right? The context is up and running. We can get our handler from the context. But during a cold start, this happens as well. We have this new box here which says init, and that is when Spring does its initialization. And when Spring initializes, it does a bunch of things. It needs to figure out how your application fits together and initialize everything. And I want to know, how long does this take? I want to know if our outlier in the beginning, maybe that was just a fluke. Or is it consistently around 6 seconds? So how do we benchmark cold starts? You can't just throw a bunch of requests because you will get mostly warm results. So after talking to Mark over there, I redid my benchmarks, and I came up with this approach. So the first thing I do is I update the configuration. Before, when I first did this, I did a redeployment, but it takes a long time. Now I just update an environment variable because that changes the configuration. And then we wait for the Lambda to be ready. We publish a version of that Lambda, and then we wait for that version to be ready. There's a lot of waiting in doing cold start benchmark, by the way. Once the version is ready, I quickly throw out 30 simultaneous requests, and I gather the results. And then I check the log tails for all these results. So any result that contains an init duration in the log tail, I keep those, because that was a cold start. And if it doesn't contain an init duration, that was a warm run, and I throw those away. And then I just repeat these until I have 200 measurements. So let's plot those 200 measurements. And we can see that 6 seconds is, that's around what it takes to start this Lambda cold. And I don't like that. So we need to do something. We need some antifreeze for our code. Now, I don't know what antifreeze is in software. I just like the analogy. I kind of like cars. But to try to figure out what antifreeze would be for code, let's look at what Spring does. So this is not really how it works, but we can pretend this is what happens in these nice 3 steps. So the first thing that happens is that Spring scans the class path. It looks through all your jar files or your classes, and it tries to find interesting classes based on what they're annotated with, right? Because that's what Spring cares about. Spring wants annotations, and it wants to know which classes are annotated with what, and what they look like. And then it takes all this information, it tries to figure out, okay, how does this application fit together? What do we need to do to make this application run? And then it does that. This sounds kind of wasteful, right? Every time we start up, we analyze the application and we figure out how it fits together. It should be the same every time, right? Because it's the same application running in the same environment, but we still do this thousands of times during the course of our application. Can we not do that? Well, there is another library called Micronaut. It was written or conceived by Graham Rosher, which is the guy who initially wrote Groovy on Rails, later renamed to Grails, because Ruby on Rails didn't like the Groovy on Rails thing. Grails is based on Spring, so he's quite familiar with Spring, but he decided that there's a better way to do this, and so he launched Micronaut. And if we look at the Micronaut webpage, we have this nice quote, the Micronaut way. And it says that your application startup time and memory consumption aren't bound to the size of your code base, resulting in a monumental leap in startup time, and that's my emphasis, blazingly fast throughput and a minimal memory footprint. And this is what we're after, right? We want a monumental leap in startup time. So let's rewrite our application in Micronaut. What would that accomplish? Well, if we look at Spring, we have compilation phase when we compile on a computer, and we have at startup time in Amazon Lambda during our cold start. Spring does dependency injection, which is all the analysis, scanning of class paths and everything. And then we have the initialization where we talk to DynamoDB and we're ready to run. When we do Micronaut, Micronaut does this a bit differently. So Micronaut hooks into the Java compiler via something called, I think it's the Annotation Processing API. And it tells the Java compiler that whenever you hit one of these annotations, I want to know about it. So Micronaut can then, they do all their analysis while the Java compiler is compiling your application down to bytecode. So all of the analysis that Spring does here, that's already done once you have your jar file and baked into the jar file. So what we essentially have is we have a hardwired application as if we would do it without dependency injection. But we get to program as if we have dependency injection. And this then should revolutionize our startup times, because we don't have to do as much dependency injection during startup. We just has to do the initialization. We need to talk with DynamoDB and create our classes, create our objects. So Spring and Micronaut, as I said, Graham Rosher has a lot of experience with Spring, so they're fairly similar to work with. All I had to do was I need to change this implements function in Spring to extend Micronaut request handler and change some of the annotations over here. We use inject instead of autowire. You can actually use inject in Spring, but whenever you read Spring documentation, they tend to use the autowired annotation. You can use the inject annotation in Spring as well. But we use introspected instead of component. If we go to the user repository, it's basically the same story. The code is the same, we just change the annotations. We use singleton instead of component. We use property instead of value. Really easy to change. Might be harder if you have a larger application, but if you go from Spring to Micronaut, it will feel familiar. You will recognize yourself. So, yeah. It doesn't have as many modules as Spring. No, it has lots of modules, just not like Spring has an insane amount of modules. But yeah, it will cover most of the bases. And it's easily extendable as well. If you need to use your own modules and do your own wiring, you can definitely do that in Micronaut. So let's benchmark this then. Let's do the same benchmark we did with Spring, but let's do it with the Micronaut Lambda and see if it gives us a monumental leap in startup time. And it doesn't. We save around half a second. I mean, that's good. Half a second is a long time if we talk compute. But we're still about 5 seconds here, so we're still about 20 seconds for our poor coffee drinker who wants to go to the theater. We can't have that. So what's the real problem here? It's obviously not the dependency injection at runtime. I mean, removing that certainly helps, but that's not the big part. So it turns out this isn't the whole story. We need to put another box in here, and it looks like this. So if you can't read this text, it says just-in-time compilation. And this is what the JVM does. When it reads your class, it loads your class, it does another round of compilation to compile that class into code that it can actually execute, which is specific to the machine that it's executing on. And if we add this to the runtime compile time overview, it looks a bit like this instead. So we have our compile times, which is very slow. And in the runtime, we have dependency injection, and in it is really just a small slice of the time it takes for our application to start up. The real deal here is the just-in-time compilation. So can we get rid of that? Well, we can't. Java needs to do its compilation because we only have bytecode. We only have Java JVM bytecode, right? We need to go to the native executable stuff. But we can cheat. So last year, Amazon launched something called SnapStart. And I think this is a pretty genius idea, actually. So what they do is that when you publish a new version, and that's why we publish a version when we do cold starts, they start the application, and they load your handler function, which means that the JVM does all the class loading, all the just-in-time compilation, and some initialization. And then they pause the virtual machine and they take a snapshot. If you ever played emulation games, you can take snapshots of your emulator and you can go back and cheat. Like if you mess up, you can just restore to the previous state. It's basically what they do here. So whenever you need whenever the function isn't running, whenever Lambda decides they need a new instance of your function, well, they just resume that snapshot on a different machine. So they clone your application state. Instead of letting it start again, they just take the already started application and they clone it. And that means that all the initialization is done, all the dependency injection is already handled, the just-in-time compilation has already happened. So we should just go on from warm. So everything should, in theory, be warm. We have some small time to restore the virtual machine. So let's see how long that takes. and that gives us around a second. Now, Spring and Micronaut is fairly even here, as you can see, because dependency injection has already happened, right? It doesn't matter if we do the dependency injection during compile time or runtime here, because that's already happened in the snapshot. Now, there are some drawbacks with snap start, which is why this is not the end of the presentation. If you're happy with the second, yeah, you could go and see another presentation, because I think this is perfectly fine for some cases. But there are some drawbacks. So one of them is that you need to dry run everything in your application. So to get this to work, the first time I did this measurement, we ended up around 4 seconds, because I just enabled snap start, and I had my original code, and I ran that, and we had a 4-second cold start. So what I had to do was I had to add this code to my handler. And this basically does what the application does, so we ensure that all the classes are loaded and initialized and compiled. Because if I didn't do this, well, the DynamoDB and all the secure socket layer and HTTP classes maybe wouldn't be loaded. So that would be done in runtime. So you need to make sure that you exercise all the code paths in your function before the snapshot is taken. And you do that by implementing an interface called resource, I think, which is part of a package called crack. I don't know why they named it after a drug, but yeah. So what we do is we add some code to exercise all the code paths in our application, and ideally we should do read-only stuff. We don't want to write to our database because we don't want to change state whenever we cold start something or whenever we snapshot something. So this is something you need to think about. It's really hard to test this. Like, how do you write a unit test that makes sure that your cold start time is good? It's kind of hard. So this is there's a trial and error involved in this. But once you have it in place, hopefully you don't have to mess with it that much, unless you add new code paths. And then you will see that by seeing that your application is starting slow again. Another thing is, this is old gaming hardware, right? Lambda only supports LTS Java versions. So that's today means Java 11 and Java 17, which might be fine. But if you want to play with the new toys, say you want to use virtual threads, which is Java 19 and up, you have to wait to Java 21, which is the next LTS version. And then there's probably some delay between when Java 21 is released and when Amazon supports it. And there might even be even more delay before they support it for Snapstart, because they need to do a lot of verification tests and maybe patch it to make it work. But if you're fine with Java 17, that's not a problem, right? So another thing, how many in here know what this is? Almost. This could be a DTM car, except it's not German. This is the World Endurance Championship. So this is a Ferrari 488 in GTE spec. It's got around 500 horsepower, weighs about 1,300 kilos. That's a fast car. That's way faster than my Volkswagen at home. This is an Audi R18 e-tron Quattro. That's a hybrid. It's got 400 horsepower, rear-wheel drive, but it's also got a 400 horsepower electric drive on the front wheels. So it's got 900 horsepower, and it weighs around 900 kilos. It completely destroys the Ferrari on the track. Like watching these two out of a corner, this looks like a Fiat or something. It's crazy. So, who in here are happy with the Ferrari? Yeah? Well, I want the Audi. I really want the Audi. I like the speed. So how can we get the Audi? What's an Audi? And my analogies are starting to break down, but I like cars, so whatever. Well, we can try something different. We know that the problem is the just-in-time compilation, so maybe we can do something that just doesn't do just-in-time compilation. And I know of one thing that I also like, not as much as sports cars, but I like Rust. Rust is a compiled language, which means that it compiles down to native binaries, and yeah, that's it. Then you just run it. There's no just-in-time compilation whenever it starts up, because it's a native binary. There's no virtual machine that needs to do things. Rust does look a bit different from Java. This is part of the function. This is the meat of the function. Sadly, I don't know of any dependency injection frameworks for Rust. At least none of that is any good. There are some experiments, but nothing really mature. So we need to hand-wire everything. Luckily, this is a very simple function, so that's not a problem. But it might be cumbersome in bigger applications, especially if you're used to like the dependency injection paradigm. But yeah, this is basically what we do. We get our event, we get our context, we load the configuration, we create a user object with a unique identifier, we connect to DynamoDB, and then we put the item and we return the user. Nice and easy. Essentially what Java applications does, but with less indirection. DDD fans doesn't like this because this absolutely is not domain-driven design. This is everything in one function. But let's benchmark this. And we get this. So this is actually around 40 milliseconds. This little outlier here is 80 milliseconds. That's a great outlier. So actually, this Rust is faster in cold starts than Java when Java is warm. Now think about that for a minute. Rust is that's our R18 Quattro right there. So are there any drawbacks to Rust? No, of course not. I like Rust. It's my language of choice, but I'm realistic as well. Rust isn't perfect. So the major sticking point of Rust, I think, is that it's a different language and it's maybe not that easy to grasp. There is definitely a learning curve to Rust. It may look fairly similar, like you have all the curly braces and the functions and whatnot. But when you start digging in and we start learning, you will run into problems. It's a different way of thinking. There isn't really any object-oriented programming. There's no inheritance by any means. And you will run into problems with something called the borrow checker. So the borrow checker is the memory model in Rust, and it's what sets Rust apart from everything else. But it also means that you need to figure out how to work together with the borrow checker, because it will completely mess up your way of thinking if you just go in and start programming as if it was Java. You need to think about memory management, memory ownership. You don't have to think about destroying and allocating objects as you do in C or in C++. Rust does that for you, as long as you adhere to the rules. So you need to be comfortable with the rules. And that takes time. I think it took me about 6 weeks of writing production Rust before I stopped getting frustrated with the borrow checker. So that's something to keep in mind. But I still think it's worth it. There's another problem, though, and that it's Rust is fairly young. It's only like 5 years old or so, and there's a lot of libraries that are still very immature. Like Java's been around for probably as long as I'm old. There's a lot of maturity in the libraries. There's a lot of libraries. If there's something you want to do, you could probably find a Java library for it. In Rust, not so much. Where you have 3 or 4 alternatives in Java, there's sometimes maybe half a library in Rust. So sometimes you need to do stuff on your own, or you can find something that's very unstable and that changes between releases, which means, yeah, whenever you update your dependencies, you have compilation errors because they decided that they changed the API again. So anyways, I thought this talk was about Java, right? Why am I talking about Rust? Well, I'm talking about Rust because I like Rust. So I take every opportunity I can. But also because I want to show what happens when we don't do just-in-time compilation. Because that's the problem, right? So can we do Java without just-in-time compilation? And it turns out that we can. There's a project called GraalVM. I think it originated as an intention to be part of it actually was part of the OpenJDK for a while. They removed it again. But GraalVM was a project, or is. The main goal was to make Java self-hosting. And a self-hosting language is a language that compiles itself. So C is a self-hosting program or language because the C compiler has multiple C compilers, but they're often written in C. You write a C compiler in C that compiles C, self-hosting. Rust has become self-hosting. The original compiler was written in C++, I think, or C. But they eventually rewrote the Rust compiler in Rust. So now you write Rust to compile Rust, which means it's self-hosting. But you can't do that with Java, right? Because Java runs on the JVM. So you can't write the JVM in Java, because that would mean you would have a JVM to run the JVM to run the JVM, and then you will stuck in some sort of recursive loop. And that leads to a Stack Overflow. Huh? Yeah. But you can't do that over and over again. Because eventually, something needs to execute whatever is at the top, right? So the intention was to, let's do away with the JVM, right? Let's natively compile Java, so we can rewrite the compiler in Java and have it compile itself to native bytecode, which we then can use to write the JVM in Java. And they did that, and they decided that this is very, very complicated. Let's not do that anymore. Let's just focus on the native compiler. GraalVM does a few other things. You mentioned Truffle, and that's the polyglot programming over here, which means you can mix and match programming languages in the same application. You can use Java, Python, JRuby, JavaScript in the same application, compile it to one application, and you won't notice in the end that there are different languages in your application. I've never used it, but it sounds useful. High performance, yeah. Who doesn't say they have high performance, right? Everyone says that. But we're interested in this. Ahead of time native image compilation, which is what Rust does with Rust applications, but we do it with Java. So we get a Java binary from our Java application. We get a native binary. So that means that this here, that we've seen before, turns into this when we have GraalVM and Micronaut. So Micronaut does the annotation processing together with the compiler, and then Graal does its thing with the native compilation, and then we don't have to do just-in-time compilation anymore. We just have to do the small dependency injection and the init when we start up. So let's benchmark this and see where we are. Right here. That's 200 milliseconds. And I'm happy with that. It's not an R18 e-tron Quattro, but it's way faster than a Ferrari anyways. Maybe it's something like the Rebellion R13, which is not a hybrid. Still a really fast car. It's basically the Audi without the hybrid drive and some more horsepower to compensate. But I'm happy with this. This is what I promised in the title, right? This is 0.2 seconds, so you all know I'm done. At least with the Lambda journey. So are there any drawbacks to GraalVM then? Well, there is. And the first one is you're compiling, right? Well, it turns out that native compilation takes a way longer than just-in-time compilation. So just-in-time compilation takes around 6 seconds, 5-6 seconds. Well, native compilation takes around 2 minutes. So the compiling the Micronaut Lambda with just a regular Java compiler, that's around a second on my laptop. Native compilation with GraalVM, 2 minutes and 20 seconds, give or take. And that's every time you compile. So when I compile my Rust applications, it caches all the results. And whenever I make a small change, like the first compilation maybe takes 2 minutes, but whenever I change something, it just has to recompile that. So it adds like incremental compilation, maybe 6 or 7 seconds, right? That's fine. With Graal VM, it doesn't happen. Every time you make a small change, it's another 2 minutes waiting for it to compile. Or you can short-circuit this by doing most of your development on the JVM. You can run your tests on JVM. You can do whatever you do locally on JVM to get that quick feedback loop that you're used to with Java. And then when you deploy, you do a native image compilation. But it's also very important that you run your tests in native mode, because there are differences between running on the JVM and running native. Graal does a lot of stuff when it comes to reflection, because it doesn't support reflection. So it needs to basically, you need to tell ahead of time what kind of reflection you want to use, so it can bake that into your native image. And yeah, that means that some things might work differently on the JVM than it does in the native image. So you need to run your tests both. You probably run your tests in the JVM because it's fast, but you also need to run them in a native image to make sure that it actually works in the real world. Another thing is that your tools, they don't no longer work. We used to like the Java debugger, we used to Visual VM, maybe you use some introspection framework like New Relic or Splunk. Yeah, they don't work with the native image anymore, because there's no JVM to hook into, right? There's no JVM APIs to talk to, it's just native binary. So debugging happens in GDB, the GNU debugger. And, well, IntelliJ IDE doesn't support GDB, it just supports the Java debugger. So you need to change it to a different IDE. So you go to something like CLion, which supports GDB, but that doesn't support Java. So at least in the JetBrains ecosystem, there's not a good way to develop your code and debug it natively in the same IDE. Visual Code can probably do this, because, yeah, but I never gotten along with Visual Studio Code, so I wouldn't know. It does, yeah. Yeah, that's good. But if you're an IntelliJ user, this might trip you up. Again, you probably do most of your debugging on the JVM, but if you have bugs in the native-only mode, then yeah, you need to debug them somehow, and that means other tools. And another thing is what I talked about earlier, and that is that Micronaut does a lot of magic for you with Graal VM. So Graal needs to know about all the reflection that needs to be enabled in your native image, and Micronaut kind of tells it that. It reads all your annotation and it turns that into the specifications that the Graal compiler uses. But once you venture outside of Micronaut to something that Micronaut doesn't support or know about, you're on your own. You need to write these specifications, you need to figure out, okay, so this class should be initialized during native compilation, this should not. You need to tell Graal all about this, and this is a lot of trial and error. You wait 2 minutes, you get a compiler error message, you wonder what's gone wrong, you try something, it gives you a hint that something was initialized that maybe shouldn't, so you try to not initialize that via writing some specification, and you wait another 2 minutes to find out if it worked. It's slow, it's boring, and it's a problem. Another thing is that we're used to Java being this, I think it's write once, run everywhere, right? You write your Java code, you compile that, and you distribute it to jar files, and everyone can run it. Yeah, not with Graal VM, because you're doing a native compilation, right? Which is machine specific. So what I compile on my Arch Linux laptop, which runs a very recent kernel, a very recent version of glibc, won't work on a Mac, won't work on a Windows machine, might not even work on a different Linux machine. Because if you go to like a Red Hat Enterprise Linux, they have a different version of glibc. So my native compile will look for glibc, 2.6, and they have 2.2, app won't run. So you need to compile for every target you intend to run on, and there is no such thing as cross-compilation. So you can't compile on a Mac natively to a Linux target, for example. You need to do that in a Docker image, which Micronaut handles for you. The Micronaut Gradle plugin handles all this for you. So when you ask that to compile a native Lambda image, it spins up a Amazon Linux Docker image, compiles in there, and you get something that works on Lambda. So for Lambda, this isn't really a problem because the tooling solves it for you. But if you want to use this for other stuff, for maybe containers, this is something you need to be aware of. You can't just take any image and run it anywhere. The architecture and the operating system has to match. So some honorable mentions here to end. There's a thing called Quarkus, which is very similar to Micronaut. It's from Red Hat. You can use that instead of Micronaut. It does the same thing when it comes to GraalVM and the head of annotation processing during compile time. I haven't, but they should be very, very similar to Micronaut in a native image because it does the same thing. It's just a different library. They do things a bit differently, so it's not as familiar if you come from Spring as Micronaut is, that doesn't have to be a bad thing. It's just that I'm used to Spring, so I prefer Micronaut. You might not. Give it a shot. You did? Did you like it? Yeah? Yeah, it's okay. Yeah. There's also Spring Native, or it used to be Spring Native. Now it's actually a part of Spring Boot 3, I think. But I wouldn't recommend using this because it means that Spring needs to go from runtime dependency injection to compile time dependency injection. And that comes with a few limitations. So everything that you're used to doing in Spring might not work when you compile it statically and you do the annotation processing during compile. You might get this to work, you might not, depends on what features of Spring you use. I would prefer to go Micronaut because they don't have the caveats. Everything in Micronaut works with native compilation. And so to end this, I would like to give you this. So this is Ronnie's flowchart for thawing your lambdas. So we start here, and the first question we ask ourselves is this really an issue? Because maybe it's not. At my last company, we had a Java Lambda written in Spring. It was running once a day, nightly, reading from a database, preparing a report for us that we read on our daily stand-ups. I think it took like 30 seconds to start, but who cares? It ran at 2 in the morning, and we needed to be done by 8 in the morning. That's 6 hours of runtime. Who cares about 30 seconds, yeah? So maybe you don't have to fix this. Usually, whenever it's not user-facing code, cold starts isn't a problem. So there's this expression, I'm sure you heard of it. It says, if it ain't broken, don't fix it. Yeah, I would like to rephrase that and say that if it doesn't add value, don't do it. If it's not a problem, just leave it alone. But let's say it's actually an issue. This is a user-facing problem. This is a user-facing function. Would you consider switching languages? Will you join me on the dark side in Rust? That's a good option, I think, because you will get performance out of that. Rust is blazingly fast. You could also look at Go. Rust and Go are probably on the same level when it comes to performance. TypeScript, Python, Ruby, slower than Rust and Go, but quicker to cold start than Java. But I would mostly look at Rust and Go if I were considering switching languages. I don't bring up JavaScript because, I'm a weird. If you want to stay with Java, which I can understand, have a look at Micronaut. It's similar to Spring. Look at how complex would it be to port your application to Micronaut? Or if you're starting out fresh, just go with Micronaut from the get-go. Learn a new library. It doesn't have all the baggage that Spring has. I mean, Spring is ancient. There's a lot of backwards compatibility and a lot of just baked in architectural decisions that maybe aren't that relevant anymore. Micronaut is fresh, is leaner, I think. So try that out and go with GraalVM native image. And if you don't want to leave Spring, well, there's one option left, and that's Snapstart. And that's a good option. I mean, if you're okay with around a second, I think it's fine. You might be able to tweak it and make it even faster. I know you can just, I ran all my benchmarks at 256 ROM. You can just increase the ROM, and the cold start speeds will increase. But I don't like wasting resources, so I prefer to keep my ROM usage as low as possible, because in the worm case, more CPU power isn't going to give you that much more performance, because we're mostly network latency bound. We don't do a lot of heavy computation, so I prefer to limit my lambdas to whatever memory they actually need. And that's it. So thank you for listening to me. And if you have any questions, please.